Hello friends, welcome back again for the presentation on work hardening or strain hardening. In the last lecture, we had seen the effect of cold working on the properties of the material. Now, in continuation to the last lecture, we'll be studying what happens after heat treatment called as annealing is introduced because we need to further plastically deform the material beyond the limit. So we cannot do it at an instance. So because the material may crack and fail. So we have to introduce a heat treatment called as annealing. So that is the concept what happens actually because of annealing that we are going to study in this lecture. So with cold working, metal becomes hard and brittle, and hence it is not possible to work them beyond a certain limit without cracking. Therefore, if cold working is to be continued, the metal must be made soft and ductile. So initially, when we start the cold working of the operations on the particular metal, the material is soft and ductile. So again, after cold working, we have reached this stage. We cannot further deform the material beyond this stage because it may crack. But our plastic deformation has not happened. We still want to plastically deform also. So for that, we should make the material again soft and ductile. That is, it should have this initial property so that with whatever is the plastic deformation happened up till this, we can retain that and further we can plastically deform the material once the structure is changed. That is, whatever has happened before after cold working, we should come back again whatever it was before cold working. So we should make the material soft and ductile by some suitable heat treatment so that further working or reductions can be done without cracking. So this word is very important, without cracking. The heat treatment which is used for this purpose is called annealing. Now, annealing is the heat treatment in which the purpose of annealing treatment is to make the material soft and ductile, obviously. It consists of heating the material. Now, heating, we have to heat the material above the recrystallization temperature, that is the lower critical temperature. We'll study this in the iron and carbon equilibrium diagram in the coming units. That what do you mean by lower critical temperature? So it is the temperature with respect to the iron carbon system. It comes out to be 727 degrees Celsius on the iron carbon equilibrium diagram. So annealing, it consists of heating the material above that temperature, and it, most probably it is heated above 910 because we have to eliminate the other phases. Sorry, being coming into the microstructure. So we have to avoid that other phases intervening in the microstructure. So we normally heat it above 910 degrees Celsius in case of a certain category of materials. So heating, then after heating, we have to soak the material because at this temperature, we want the temperature to be maintained throughout the cross section, that is at the center core as well as at the outer surface. So we have to soak the material so that uniformity is maintained throughout the cross section. So that temperature and above the excellent temperature, holding at this temperature for a definite time, that is called as soaking time. Now this soaking time is usually 45 minutes to 1 hour. It depends upon the section thickness of the material. So usually 1 hour, and cooling to room temperature. Now this cooling happens very slow. So what we are doing is we are heating the material in the furnace itself, and after the soaking time, that is after 45 minutes or 1 hour, what we are doing is we are switching off the furnace. Means heat addition is stopped now at this point, at this juncture, and now we are not adding any heat. Furnace is switched off, but without opening the doors of the furnace, we allow the material to cool in the furnace itself. So it takes a lot of time to cool the material to the room temperature, and that is obviously the purpose of annealing, that a very soft ductile structure is to be obtained, but for that the cooling should be very slow. As in how the cooling cycle increases, that is, if we go on increasing the cooling, we'll see that material will start becoming hard. So that is how it is related to the softness and ductility, because we are cooling in the furnace itself and allowing the temperature to settle down to room temperature. So it will take a lot of hours. It might take days, day or two, 24 to 48 hours to bring down the material back to the room temperature. So that much slow cooling is required, and we see that with the help of this annealing treatment, the material becomes soft and ductile. Now, property changes and structural changes which occur due to heating a cold work material are shown in the figure. The change occurs through recovery, recrystallization, and grain growth. Now, here in this figure, we can see the material. What happens after annealing is cold working and annealing is starting material with low dislocation density. So this was our initial material. which was having the low dislocation density over here, fought out material on which we started the cold working operations. So these dislocations are shown over here. Now figure B shows cold work material has greatly increased the dislocation density. So see, because of cold working, plastic deformation to occur, dislocations has to multiply, or dislocations move from one plane to another. So that is how both the theories apply, and we see the number of dislocations are increased because of the cold working. Now in figure C, annealing we have introduced in between, so that beyond this we cannot plastically deform the material. So annealing is introduced. So after annealing, the what happens is the first stage is recovery. So recovery leads annealing leads to recovery. So you can see there is certain annihilation or the polygonization being taking place. Then in so you can see the dislocation density slowly and gradually it has started reducing. Now and further the next stage of annealing, that is recrystallization, further annealing leads to the nucleation. So during recrystallization the first nucleus formation starts, and these nuclei they grow into the formation of grains. So further annealing leads to nucleation and growth of new grains. Again the dislocation density has reduced, and in the last figure we can see that is the grain growth. Fully recrystallized metal with new strain-free grains are obtained, and this again these grains develop and grow by virtue of the smaller grains surrounding in the surrounding vicinity area, that is called as grain growth. So this phenomena can be explained with the help of graph also. So we can see property and structural changes during cold working and annealing of metals. So this graph very clearly indicates or explains what exactly is happening. So this is our initial material, which is having a dislocation density, which is a equiax polygrain structure having a dislocation density of 10 to the power 4 to 6. So after cold working, we can see the dislocation density has considerably drastically increased. It has reached 10 to the power 11 to 12. And look at the grains. The grain structure was equiax polygrain before cold working. So after cold working, it is elongated. It is distorted grain structure. Now we have introduced annealing in between. So this is annealing. Annealing shows the developments in three stages. So first one is the recovery, second is the recrystallization, and third one is the grain growth. So deliberately we have marked the start point of the properties. Property number one, that is hardness, and we see that after recovery, recrystallization, and grain growth, denoted by the red dark line, it is almost appearing to the same level of the property which was initially before cold working. So in recovery, there is no considerable change in the hardness, no considerable change in the tensile strength. Slight internal stresses are reduced because of recovery, and the electrical resistivity also is slightly reduced in the case of recovery. Whereas the property number 5, that is corrosion resistance, it has improved because of recovery, because internal stresses are getting reduced, so corrosion resistance has improved. And the last one is the ductility. So ductility almost remains the same because there is no considerable change in the tensile strength or hardness. Now in recrystallization, you can see there is major drop or major enhancement in what is the desired. So hardness drastically dropping down, coming down to its original level, tensile strength coming down to its initial level. Almost same applies for internal stresses and the electrical resistance. And look at the corrosion resistance. It has almost reached its initial value in yellow colored line. And the last dark blue color line, you can see almost reached the initial value that is related to the ductility. And finally the grain growth. But look at the dislocation densities. So after recovery, and you'll find the dislocation density of the order, uh, it is almost similar, but in between the recrystallization, you can see 10 to the power 7 to 8. So here also 10 to the power 7 to 8, we see there is a reduction in the dislocation density. Now here nucleation has started in the recrystallization process, and these nuclei, they develop and try to form the grains. And look at the dislocation density. Here after recrystallization, the dislocation density is almost similar to that of the material which was before cold work material. That is, it has reached 10 to the power 4/6. And this was our objective, that we wanted to reduce the dislocation density so that further deformation, plastic deformation on the material can be done. So that is how 10 to the power 4/6 means as good as your initial value. And last is the grain growth, in which these grains which are developed after recrystallization, new grains are formed. They grow by virtue of the smaller grains surrounding the vicinity area, and this grain growth is shown in the figure. So at the end of grain growth, again the dislocation density is 10 to the power 4 to 6. So that is how we made the material soft and ductile. So one by one we'll see what happens in recovery, recirculation and grain growth. In recovery, in this region there is no appreciable change in microstructure is observed. The grains remain distorted and hence mechanical properties such as hardness, tensile strength and ductility do not change appreciably, and they can be assumed to remain the same as that of the cold work metal we have seen in the graph also. However, due to heating, some imperfections like vacancies and interstitials existing in the slip bands may get eliminated, and the dislocations of opposite sign may get annulated. Also, some dislocations may undergo rearrangement in the lattice. So there is a phenomena associated with recovery, which is popularly known as polygonization, which is shown in the figure also. So polygonization has been observed, that is dislocations of the same sign align themselves into the walls. So you can see of the same sign, they align themselves into the walls to form small low angle subgrain boundaries. So low angle boundaries of dislocations are formed. This leads to pronounced changes in the internal stresses, electrical resistance and corrosion resistance of the material. Now coming to recrystallization. In recrystallization in this region, old distorted grains are replaced by new equiexed, stress-free, strain-free grains by process of nucleation and growth. That also we have discussed when we discussed on the graph. This occurs by recrystallization process. As the name suggests, recrystallization. So nucleation occurs at these points of high energy, and subsequently these nuclei grow at the expense of old grains. The microstructure at the end of recrystallization process is much similar to the original structure, that is similar to the structure prior to cold work. The grains become equiexed. Again, whatever the distorted grains, elongated grains, they become equiexed, and the dislocation density gets reduced to a value characteristic of strain-free material. We have seen almost 10 to the power 7, 8, and then at the end 10 to the power 4 to 6, which was the dislocation density of the material which was before cold work. So due to the change in microstructure, all the mechanical properties are changed and become almost similar to that of the original material. So we have seen the drop down in the graphs and two properties having some increase in the graph. So they try to match the initial levels, original levels, with subsequent increase in corrosion resistance and corrosion resistance. Electrical resistance also goes to its original level. These property changes are shown in the figure of property and structural changes during cold working and annealing of metals, the graph which we had seen earlier. Now, recrystallization, this does not occur unless the degree of cold work is sufficient and temperature is sufficiently high. So for small degree of cold work, we will not see appreciable changes, but we need to have some degree of cold work, that is, it should be sufficient enough and the temperature should be sufficiently high to see the recrystallization to occur. Now, degree of cold work is defined as the percent reduction in cross-sectional area during extrusion, wire drawing, forging, rolling, or similar working operations, and hence this is calculated as a difference of area, that is a ratio of area, AO minus AF. That is, AO is the original area, AF is the final area divided by AO. During rolling, the width does not change appreciably, and hence this becomes approximately equal. That is TO minus TF upon TO. Whereas TO is the thickness of the sheet before rolling, and TF is the thickness of the sheet after rolling. Now coming to the critical degree of cold work, the minimum degree of cold work necessary for recrystallization to occur is called as the critical degree of cold work. As we discussed over here, we need sufficient degree of cold work for recrystallization to occur, and temperature should be sufficiently high. So the minimum degree of cold work necessary for recrystallization to occur is called as the critical degree of cold work, and this is of the order of 2 to 3% for most of the metals and alloys. For a material with a given degree of cold work, the temperature must be sufficiently high for recrystallization. The temperature at which a metal or alloy with a normal degree of cold work completely recrystallizes. Completely means almost 95% is required. So that we call as completely recrystallizes in a reasonable period, that is usually 1 hour, is called as the recrystallization temperature of metal. Now we'll see there are some factors. So recrystallization temperature of metal is a function of the following factors. Now first one is the melting point. Higher the melting point, higher is the recrystallization temperature. Degree of cold work. Higher the degree of cold work, lower is the recrystallization temperature. Then grain size. Finer the original grain size, lower is the recrystallization temperature. Purity of metal. Presence of soluble impurities or addition of small amount of soluble alloying elements, they raise the recrystallization temperature. But the presence of insoluble constituents such as the copper oxide in copper does not noticeably affect the recrystallization temperature. And the last factor is it is the function of heating time. Longer the heating time, that is with less heating rates. This is important. Although heating time is longer, but the rate of heating is less. Recrystallization occurs at lower temperatures. Survey of recrystallization temperatures of large number of metals and alloys, they indicate that recrystallization temperature of most of the metals and alloys are in the range of 0.4 to 0.6 of their melting temperatures. Normally, we take the value as T recrystallization equal to 0.5 times the melting temperature in degree Kelvin. So they are approximately half of them melting temperatures in degree Kelvin. That is T crystallized is equal to 0.5 times Tm. TMP, that is melting temperature in degree Kelvin. Now, I would like to summarize this topic. So, in this lesson, we have learned about the effect of cold working and annealing. So, predominantly, we focused on what happens after annealing, because effect of cold working we had focused in the earlier lecture also. In annealing, it is done in three stages. The first one being the recovery, in which we understood the concept of polygonization. Then recrystallization, in which we discuss about the recrystallization temperature, the degree of cold work necessary for recrystallization temperature, and the recrystallization temperature. And recrystallization temperature as a function of certain factors. So we discussed all the five factors. Then came the grain growth. Thank you.